Good morning. First of all, I would like to thank the organizers for having invited me to this very nice conference and the place. And today I would like just to describe some activity of my labs concerning to the possibility to visualize some interesting phenomena by using quantum optics. This is one of the activity of our labs. Another important activity concerns the measurement in weak coupling regime. We made experiment regarding sequential weak values. We realized the first protective measurement experiment and so on. But today I would like to mention this other activity. You know that there are phenomena that one cannot really study experimentally because they concern extreme situations which cannot be realized in the labs. For example, Hawking radiation, or Uro effect, or closed time like curves and so on. What one can do in the lab is trying to search for similar phenomena that can somehow give some visualization of these other phenomena. Now, for example, Hawking radiation, there was some simulation of Hawking radiation by using Bose-Einstein condensate. And today I would like just to mention this activity, considering two examples related to time. Now, time is something in physics which has different interpretation in different theories of physics. Of course, in Newtonian physics, we have an absolute time, just a sequence of events. And this is absolute true and mathematical time with an arrow time. And somehow also in non-relativistic quantum mechanics, we have something very similar, just a parameter. But when we go on special relativity, of course, situation changes. We have the time is some sort of fourth coordinate. It depends on the time interval on the observer. We can define a proper time, which is the time that an observer sees on a clock at rest, and to write the proper time for a certain observer. In general, relativity situation is even more complicated. Now time depends also on the gravitational field. We know that the clock in a strong gravitational field is slower than a clock without gravitational fields. And these effects are relevant, for example, for GPS or Galileo. So time is something that is changing in different physical theories. And a particular problem of time emerged when we try to consider the whole universe. We try to consider gravity and quantum mechanics together. One of the problems derives when one trying to describe the universe with a single wave function and build, due to the constraints of general relativity, build the Wheeler-DeWitt equation. Wheeler-DeWitt equation is a stationary equation. So the wave function of the universe should be stationary. Of course, what does it mean? We see evolution of the universe. It's not static. We experience evolution of the universe. So one has to find somehow a way out of this problem. One of the possibilities was suggested by Page Wouters already several years ago, then was further elaborated, for example, by Giovannetti, Lloyd, and Maccone, and others. So which is the idea? One can have, I'm presenting here following more or less this paper of Giovannetti, Lloyd, and Maccone. You can have a global static wave function, but then you can partition the wave function in a clock and the rest of the universe. And what happens is that this global wave function can be stationary for a certain Hamiltonian, but you can observe the evolution of the rest of the universe when is referred to the clock system. So the system, the value of the observable of the clock system are giving the time of the rest of the universe. So you're partitioning the universe into two parts, the clock and the rest, evolving according to the Hamiltonian respect to the clock. So somehow you can find again a Schrödinger equation from Wheeler-DeWitt. And okay, I'm not going into the details of the theoretical part that you can find in this paper. Our idea, realized together with, in my labs, together with Lorenzo Maccone and Vittorio Giovannetti, was trying to visualize somehow how this phenomenon can happen. So we have chosen a very simple universe, 2 photons, so it's extremely simple. But this is an entangled state that eventually is invariant for a certain Hamiltonian, so the total system is not evolving for this Hamiltonian. But when you observe the evolution of one of the 2 photons respect to the values of the observable of the second photons, you have an evolution for the same Hamiltonian. So in practice, what are we doing? We are generating entangled state in polarization, psi-minus state. So psi-minus is invariant for a rotation of polarization of some birefringent element. So the total state is invariant for this specific Hamiltonian. But what you can do is to observe the evolution of one photon according to the values of the observable of the clock photon. If you do this, as I will show you, we observe an evolution. If you recompose the state and you make a total tomography, you see that the total psi-minus is not evolving. So it's invariant for this kind of evolution. This is in the super observer mode. Okay, so these are the results of this experiment. So in the observer mode, when we relate the observable of the second photon to the time measured with the first photon, which is giving the clock, you observe an evolution. But the fidelity to psi-minus for the global state with the same Hamiltonian is always very high in the sense that the global state is not evolving. Of course, this is not a demonstration of Page-Wootters, it's not an experiment really about the Page-Wootter model, but it's giving a visualization how this effect could happen. You are partitioning a global state not evolving for a certain Hamiltonian in 2 parts, the clock and the rest of the universe. And you observe evolution of the rest of the universe with respect to the clock, while the total state is invariant. Then you can try, okay, this was a very simple experiment, just a 2-time clock. You can have several time measurements. We made a second experiment more recently, always with Lorenzo. And here the idea was simpler. We didn't have really entangled photons, just a laser with a long coherence time. So if you perform the experiment in a dimension which is much smaller than the coherence length, so everything is coherent. So you have a super observer model where everything is coherent. But you can observe the evolution of one observable in respect to the other. In this case, are 2 degrees of freedom of the same photon. One is the position along X, which is the clock, and the polarization is the system, the rest of the universe that you want to measure the evolution. And here you can visualize several times evolution of the total system, while of course you have a super observer that since the coherence length is much longer than the experiment, see somehow an invariance. This is another possibility to visualize this phenomenon. But most of this talk will be concentrated in the most recent experiment. The idea is to consider another phenomenon that of course cannot be realized in the lab, which are the time-like curves, closed, or I will mainly concentrate in explaining what are open time-like curves. Again, you know that when you are next to an extremely strong gravitational field, eventually like a maximal Kerr black hole, the light cone can be, in general relativity, so turned that you can have a closed curve, and at the end you come back exactly in the same time and space point. So you have these closed time-like curves, which are some sort of time machines. And these are a solution of general relativity. They exist in general relativity. of course, general relativity is not a quantum theory. Maybe in a more general theory of gravitation, these will be excluded. Of course, they present all sorts of problem. Of course, in a classical case, you have the grandfather paradox, no? That you can formalize with some circuits, so you have bits, and substantially a bit can be 0, is starred if the other is 1 or not, but if this is traveling back in time, and this was 0, nothing happened, but if this was 1, then it's turning the value of himself, and then it's coming back, so somehow it's killing his father. No, and so there is a problem of consistency. But Deutsch has demonstrated that this problem of consistency can be overcome in quantum systems. So in quantum systems, you can always find solutions to this consistency equation, and this is due to quantum superpositions. But to find a solution to this consistency equation, when you are splitting your total density matrices in a part that is the experiencing the closed time-like curve, so it's the one traveling back in the past, and the one which is chronology preserving, so does not have any of these traveling back. If you try to do this introduces nonlinearity in the evolution of the chronology preserving part, and this nonlinearity due to CTC is somehow modifying what are the usual properties of quantum mechanics. So in this case, you can have perfect discrimination of orthogonal states. You can have violation of uncertainty principle. You can have violation of no cloning theorem, and you probably know if you are violating no cloning theorem, this means also that you have a superluminal communication and so on. So it's true that you can find, thanks to Deutsch, this consistency of closed time-like cures in quantum mechanics, but this is introducing all sorts of modification of quantum mechanics. So this kind of situation had also optical simulations. Of course, you cannot realize again a time-like curve in the lab, but you can somehow visualize this effect with a specific quantum optics experiment. This was done with actually some modification of this is projective closed time-like curves by Seth Lloyd, Lorenzo Maccone, and in the group of Ephraim Steinberg. And another simulation was done later by Ralph group. Now we are concentrating in trying to simulate a little bit different situation, so open time-like curves. Here we have an entangled state. One of the member of the entangled state is experiencing the travel back in time, but is not interacting with himself. But you can look to the correlation between, at this point, among the three states, the old entangled state and the one which has traveled back in time. And what you observe is that you have a violation of entangled monogamy, because, of course, at the beginning you can have the two states which are maximally entangled, but when one is traveling back in time, it's still perfectly correlated with the first one. And so you have a perfect correlation between 1 and 2 and 1 and 3. So you are violating entangled monogamy. So we have looked to the possibility to describe the situation by using a formalism that Vlatko Vedral is developing. So we have made this work with him and Chiara Marletto. The idea is to use this formalism that is developing, which is called pseudo-density operator. So in this formalism is trying to include at the same time correlation between systems in space, but also in different times. So to have a density is not anymore a density, it's a pseudo, because I will describe the differences in the properties with respect to density matrix. You have a matrix that would like to describe correlation either at the same time, but also in different times between the subsystems. So this was proposed by Blatko and others in this scientific rep. The idea is to build a general density matrix. Of course, you can decompose, if you are considering qubits, in polymetrics, and to try to describe not only correlation at the same time, like a usual density matrix, but also correlation in time. This kind of pseudo-density matrices are Hermitian. They are trace 1. The partial trace is giving you the density matrix of the subsystem at a certain time. But since you have also these time correlations, actually they are not really density matrices. They can have negative eigenvalues and not restricted, they are not positive. So they are somehow a generalization of density matrix, trying to describe also, include also correlation induced by time evolution. So why this formalism can be useful? Okay, let's try to first to see how they can describe, for example, two-time measurement on a maximally mixed single qubit. You can introduce a pseudo-density matrix in this way. You can see that these pseudo-density matrices are similarity with a singlet, but correlation here are all positive and the operator is not positive operator. So this would be the pseudo-density matrix describing a maximally mixed single qubit having measurement at two different times. Now, let us now consider if the situation of this open time-like curve. So what is happening? We have a maximally entangled state, but one of the two pairs is experiencing a time-like curve, so it's reappearing. And if you look to correlations, now of course it is maximally entangled as well with the first qubit. So you are completely violating monogamy. So how to describe with a pseudo-density matrix this system? This can be done. Actually, the system is described by a pseudo-density matrix of this form, where you have the user Pauli matrix, and this is just the identity. So this is exactly describing the correlations you are observing in this kind of situation. So this formalism allows you describing this kind of physics. And of course, you have that you are violating the entanglement monogamy inequalities. And what we have tried is just to visualize again with an experiment such kind of experiment, such kind of phenomenon, realizing an experiment where we can have the same pseudo-density matrix that I've shown you before, and to demonstrate a monogamy violation. In particular, experimentally, it is convenient to use CH-SH inequalities, and the monogamy relation at this point is given by this inequality. So this is just the setup we are producing. Of course, the experiment is not very complicated. We are just producing entangled pairs of photons. We can measure the correlations of the two photons directly, but one of the photons can be remeasured later. Of course, we must use a priori information in this case because we are not really able to realize the time travel of the photon. No? So this must be used for the, setting the second photon in a way that altogether we are the same situation of the pseudo-density matrix that I've shown you before. And we are measuring also the correlations between 1 and 2 and 1 and 3. And then we look to the possibility of violating monogamy relations. Of course, we can make a generalized tomography and to reconstruct the pseudo-density matrix. This is the reconstruction of the pseudo-density matrix. This is the theoretical expectation. The pseudo-density matrix in this case is real. So these are the real, the reconstruction of the real part of the pseudo-density matrix. There are very good fidelities with the theoretical one. The imaginary part in the theory is completely zero. In the experiment, there are, of course, small fluctuations, but they are, again, very next to zero. So the experiment really reproduced the pseudo-density matrix of our interest, and then we can look to the monogamy relations, and you can observe, again, a clear violation of this monogamy relation. I remember the upper limit was 2, and sorry, for 4, and we have several standard deviation violations of these monogamy relations for different, here we consider 1, 2, 2, 3, 1, 2, 1, 3, 2, 3, 1, 3. So the first photon is the one not experiencing the time travel. The photon 2 is the photon before entering the time closed curve, and the 3 is the one getting out from the time closed curve. Okay, before concluding, I would like to mention that with LATCO, we are also considering that maybe there are other situations where you have a similar phenomena that can be described by similar pseudo-density matrix. For example, as you know, there has been a long discussion about what is happening of information when falling inside a black hole. Then the problem is that, of course, you have Hawking radiation, which is just thermal radiation. At some point, the black hole is evaporating, but since thermal radiation has no correlation with the photons that have been emitted before, you can have an entangled pair. One photon is getting inside the black hole, the other is getting out. But when the black hole is evaporating, Hawking radiation has no correlation with the first photon. So this entanglement is completely lost. What happened of information and so on. Of course, there are several possible solutions of this information problem. They have been discussed by several scientists, including Thorpe, Hawking, etc. But a possibility is to describe this situation again with the pseudo-density matrix. So you can have a monogamy violation because you are describing the systems with this pseudo-density matrix, so the photons out and the photon in are correlated, but eventually also the photon out again can be correlated without problem with monogamy violation in this description, because it's exactly the same density matrix that I have described before. So this is still something that must be considered more in detail, but the situation is very similar to the previous one. Okay, so I'm arriving to the end of this presentation. I hope to have given you at least an idea of why it could be interesting to try to visualize these phenomena that one cannot really investigate experimentally, but at least to have a visualization with some simple experiment in quantum optics that can give some insight how to solve the problems related to this phenomena. Thank you for your attention.
Okay, thank you so much. I have a question about the last part of in the simulating on the black hole evaporation to the information loss paradoxes. You mentioned about it. That's the should density operator, should density matrices can be applied to such kind of situation.
Yeah.
But your measurement scheme is needed to the correlation measurement between the inside the black hole and the outside black hole.
So
by definition, we cannot access to the classical communication between each of us. How to do it?
Let's say the pseudo-density matrix, in this sense, the idea that we are considering is this one. At the beginning, you have the pair of two entangled photons. One is getting And they
inside.
are described by usual
Yeah.
density matrix. One
Right.
is getting out and the other inside the black hole.
Yeah.
At some point, you would like that this entanglement is not lost, but for some quantum gravity mechanism that nobody knows,
Yeah.
the correlation is maintained by the new photons emitted by Hawking radiation. So this is a third photon at the further time, and you have the first photon which is still traveling in the universe eventually,
Yeah.
and you want to describe the correlation between the 1 and 3. So the idea is to use the pseudo-density methods to describe the correlation at time 0 between 1 and 2, and a certain future time between 1 and 3, having a maximal entanglement between the two pairs, like the ones that we have described in
To verify that's the process is you need that's the coincidence of this between two. Is that one and the one photon inside is the black hole? That's the photon is that's the
No, okay,
emitted.
but in principle, you can make some non-destructive measurement and to have the correlation before it's passing the horizon. Not? So you are producing the part, and you know that it is entangled because you have measured the two photons before the second photon is passing the horizon.
Yeah.
And then you would like to measure. Okay, of course, this is nobody is even thinking to do
Right. Yeah,
an
yeah.
experiment like this, but theoretically, you can describe the entanglement of the first
Yeah,
pair
so
and the
theoretically
entanglement
that's
at the
true.
second.
Yeah. Okay, thanks.
Yeah, in PW model, they used tomography on the subsystem and tomography on the composite system. And we know that when we measure the subsystem, we surely destroy the composite system. The measurement is lying between the tomography of composite system and the subsystem. So how do you make sure that the measurement is not causing any difference on the subsystem?
No, okay, you have a matrix with a certain number of elements that you want to reconstruct, and you have a quorum of minimal measurements that allows you to reconstruct these elements. Of course, this is not completely ordinary tomography, because in ordinary tomography you have also the bound that your density matrix has all positive eigenvalues, so you cannot use here. And we have chosen the minimal number of measurements that allows to reconstruct the single element that of the pseudo-density matrix. So it's different from a usual tomography because you don't have this bound, you know, that you can use in usual tomography. I don't know if this is answering more or less what you're asking.
No, so the whole point was that. Okay. We'll
Yeah.
ask you.
Maybe we talk.
I have a simple question. Is there a notion of pure states and mixed states with this pseudo-density matrix?
Yeah, you can describe both.
It works the same way.
Yeah, of course, it's not very easy to write the general pseudo-density matrix for a complicated state eventually mixed, but in principle, yes. I have also to say that this formalism probably is not yet completely defined. No, the Vedralia is working theoretical with other people for building a clear version of this pseudo-density matrix, but still work in progress.
You're going to measure the coincidence between 1 and 2 in a non-destructive way, and then measure the coincidence between 1 and 3.
Yeah,
Is that the idea? I mean,
of course, what does it mean? That
Yeah.
You have to use compatible bases in practice, otherwise the photon would be modified by the first
Yes,
measurement.
so this is so that is why you're saying it's work in progress.
This is what I mean when I mention that one has some a priori information, because of course you cannot have the real time closed loop.
Right.
System and clock state.
Yeah,
Initially.
Page
So in that thing, you don't have initially you take a product state because your experiment involved a spatial and polarization degree of freedom, which is naturally it would be in a correlated state in your experiment.
Yeah,
so, but the system and clock, I would like to have a measurement which is controlling system and clock in some particular way, But in the polarization and spatial degree of freedom, it has its own correlation. So how would you deal with it?
Yes, probably what I have to mention is that you have the clock is the x-axis. The system is the polarization, and then you have the memory, that is the z-axis. So your birefringence is correlating the system with the memory, and what is measuring a different x, it means this means time. Okay, the different x's are different times, and you have different polarization, and you have different memories. But for the system, for the whole system, the coherence length is much longer than the positions that you are measuring, and this is introducing a global coherence of the system. So the global coherence is introduced in this way.
So I think we'll have to throw that. Thanks, Peter, again.
Thank you.